DOE CSGF Fellow Brett Larson in the field of physics at Stanford University.
Hi, I'm Brett Larson from Stanford University, and today I'll be presenting on practical leverage score-based sampling for low-rank tensor decompositions. This work actually started out of my practicum at Sandia National Laboratories and is joint work with Tammy Kolda, who's shown here. Large sparse multi-way data, or sparse tensors, appear in a variety of applications, and today we'll be specifically considering a tensor constructed from comments on the website Reddit. Reddit is a social news aggregator, content rating, and discussion website in which users subscribe to and comment in subreddits or discussion forums on a particular topic. The tensor we'll be using today comes from FROSTT, which is an open repository of sparse tensors. It is built from Reddit comments posted in the year 2015. The tensor has 3 dimensions or modes. The first is 8 million users, the second is 200,000 subreddits, and the third is 8 million words. Each element of this tensor is formed by first counting the number of times a user uses a specific word in a given subreddit, and then taking the log of this count. Overall, the tensor has 4.7 billion non-zeros, which is actually a very small fraction of the total number of elements in the tensor, 10 to the minus 8%. And the overall size of the tensor is 106 gigabytes. Now, often with tensors, we want to find decompositions of the tensor, either to get a much smaller representation of the data or to find trends in an unsupervised manner. And the most popular of these decompositions for tensors is the CP decomposition, which decomposes the tensor into rank 1 components. As to illustrate this, we'll be looking at an order 3 tensor like the Reddit tensor, and then each dimension has size n1, n2, and n3. The CP decomposition then tries to find the best model tensor that can be written as the sum of R rank 1 components. A rank 1 component is a 3-way outer product of vectors, and if we sum R of these, we say that the decomposition is rank R. Once we have a decomposition like this, we can actually arrange the vector corresponding into each dimension into what we call factor matrices. So if we take the R vectors corresponding to the first mode, the R vectors to the second mode, and so on, then we obtain the factor matrices. And these actually define the CP decomposition. So when we discuss algorithms for finding it, we'll be discussing finding the factor matrices. And to give you a better sense of what these factors look like, I'm actually going to start by showing you some of the factors obtained by our randomized algorithm on the Reddit tensor. So each of these is a component in a rank 25 decomposition. What we did is we took the subreddit word and user parts of the factors in that component and then sorted them in descending order. And here you'll see the top subreddits, words, and users. The size of the bar represents the size of the subreddit in the component, or it's kind of its influence in that component. And then the color actually of the bar indicates the frequency of that word in the overall tensor, normalized to be between 0 and 1. And what this allows you to see is words that might be kind of unique to that factor. So this first one we have, component 6 of 25, looks at international news. So you'll see large subreddits like world news and countries and continents like Europe, Canada, and India. And you'll also see some specific topics that users might have been interested in discussing in the year 2015, like the Ukrainian conflict and the Syrian civil war. Component 19 out of 25 focuses on movies and television. So in the top subreddits, you'll see some popular franchises like Star Wars, Game of Thrones, Marvel, and you'll see words that are specific to movies and television, like film and character. The next 2 components I'll show you are sports components that actually focus on specific sports. So component 15 is specifically focused on wrestling. This top subreddit here, squared circle, is so named because a wrestling ring is a square. And then you'll see some of the words related to wrestling, like wrestle, WWE, and match. And component 18 out of 25 is specifically focused on soccer. So you see soccer as the top subreddit, and then you'll see a lot of subreddits with FC, which stands for football club, for like a British football club. And then you'll see words related like goal, fan, club, and player. So these are some of the things that we can kind of get out of these decompositions once we run them. And now we're going to return to how do you actually find the CP decomposition? So the CP decomposition, the most popular algorithm for finding it is called CP-ALS, or alternating least squares. And what happens is you fix all but one of the factor matrices, you solve for that factor matrix, and then you rotate through the factor matrices repeatedly. So it's sort of coordinate descent on the factor matrices. This value that we're trying to minimize, which measures the mean squared error between each element of the model tensor and the tensor itself, is called the residual. And what you get for each factor matrices that you solve for is this prototypical least squares problem. And what I'm going to do is describe for you what each of these matrices look like. So the first, this matrix Z, is formed from the other factor matrices. It's called the Khatri-Rao product. And the important thing about it is that it's very large. The number of rows in the Khatri-Rao product is equal to the number of possible combinations of rows of the factor matrices, or order n to the d. And the structure of this matrix is going to be key for our algorithm. This matrix X is actually just the tensor unfolded into a matrix. So if the tensor is sparse, this matrix X will be sparse. And it's important that we can't afford any transform that will destroy the sparsity, because it would be too expensive to store a dense version of the full tensor. And lastly, we have this factor matrix, which we're going to be solving for. So the important thing about this prototypical least squares problem is that since this matrix Z has so many rows, the associated linear system is highly overdetermined. And so our goal in our algorithm is to apply a technique from randomized numerical linear algebra called sketching, where we sample the rows of this matrix to form a much smaller least square system that we can then solve much faster. And then we want to give an associated guarantee that the solution that we find to this smaller system will have a residual that's close to what we would have gotten if we solved the full system. And in the case of applying this to the CP least squares problem, this sampling actually corresponds to sampling fibers from the tensor along a given mode. So in the rest of this talk, I'll be presenting 3 ingredients that we had to put together to make sure that this algorithm was practical and ran efficiently compared to the full CP-ALS algorithm. So the first ingredient is using leverage scores to limiting the number of samples that you have to draw. So you can imagine that when you have a matrix, that some rows could be more important to other to forming the transformation that the matrix performs when it's multiplied by another matrix. The space that the matrix transforms into is referred to as the column space, and the leverage scores measure how important a given row is to forming a dimension of the column space. We can find the leverage scores through the SVD as shown here. And to give you kind of rough intuition, say we have a matrix, a tall and skinny matrix where one of the columns only has a non-zero element in one of the rows. This row is going to have a leverage score of 1, because if we don't include it, the column space will be rank deficient. It'll lose 1 dimension. All the leverage scores together sum up to the number of columns if you have a full rank matrix. And so each one is a value between 0 and 1 that measures how important a row is to forming a part of the column space. By using leverage scores, we can actually really limit the number of samples that we need to get this nice approximation property. But unfortunately, they're too expensive to compute on their own. Fortunately, though, we can actually use approximate leverage scores and pay some penalty in the required number of samples. This is where ingredient 2 comes in, because our matrix Z has a special structure, this Khatri-Rao product structure, and we can use that to form efficient estimates of the leverage scores of the rows of the KRP. Each row of the KRP is formed by taking 1 row from each of the individual factor matrices. And you can show that the leverage score of the row in the factor matrix is upper bounded by the product of the leverage scores of the corresponding rows in the factor matrices. And these are much cheaper to compute because these factor matrices are smaller. What we can then do is we can set our probabilities to these overestimates, and instead of sampling a row from the KRP, we can then sample according to leverage scores of each of the factor matrices and then form those corresponding rows. So we never have to form the entire KRP, which is extremely important. And the last is kind of a contribution that we added that we think can be useful across all sorts of sketching problems. So in our problem in particular, the KRP tends to make leverage scores more concentrated. And so this is an example from one of the solution factor matrices where you see that we've plotted the leverage scores on the log plot, and you can see that a lot of the weight of the leverage scores are in a few rows when we sort them and see how concentrated they are. So the problem is when you do sketching, you'll probably repeatedly sample these high probability rows over and over again. And what we proposed is what you could do instead to make this more efficient in the number of samples is you could specify some deterministic probability tau, and you could include those rows that are above that threshold deterministically. And then you can perform hybrid sampling where you sample from the remaining row, the remaining number of samples you need from the remaining rows randomly. And because you're no longer sampling from these highly concentrated ones, you'll probably get a more diverse set of samples. And this plot here just shows you on an example KRP problem from a tensor that we use in our paper that this actually can make a big difference in terms of the quality of your approximation versus the number of samples. So what this plot shows is we solve this least squares problem over and over again, and then we calculate how close our sampled residual was to the true residual. This is plotted on a log plot here. And you can see that the hybrid method, much more quickly as you vary the number of samples, gets higher accuracy on the problem than random sampling. And lastly, I'm going to return to how, when we put these things together, how this performs on the Reddit tensor. So these are runs of our algorithm, CP-ARLS, which produce the factors I showed you at the beginning. And the blue curve is the standard CP-ALS algorithm. There are 10 runs, which are the individual lines in the background, and a median, the solid line is a median calculated across all these runs. And then the red curves is our algorithm with hybrid sampling using 2 to the 17 samples. And you can see there's actually a dramatic difference. They both achieved a similar fit value, but the CP-ALS algorithm took 96 hours to run, or about 4 days. And our algorithm took about 8 hours to run, which is about 12 times faster. This shows the fit across all the different runs, which is just to confirm that we're getting the same quality of approximation out. And we see that, like I said, with the hybrid sampling, it's about 12 times faster. With the random sampling, it's about 16 times faster. And probably a large part of the difference in these speed up is we're actually using an estimated fit to terminate the randomized runs. And so there's a little bit of noise in how soon that you actually quit out of the algorithm. So lastly, there's a cool application of our algorithm to distributed data. So say you have a large tensor stored across multiple nodes. You won't be able to run CP-ALS because you'd have to be able to work with all of the tensor at once. But with our algorithm, what you could do is you can instead have a node with all the factor matrices. And then you can use those factor matrices to sample from the tensor and then pull the required sampled fibers from the distributed nodes to the single node and solve the smaller sample problem on a single node. So this algorithm, in addition to being faster, allows you to work better with distributed tensor data. So in summary, we've presented 3 ingredients for how to work with sketching for sparse tensor problems. The first is that sampling by the leverage score allows us to minimize the number of required samples to get the good approximation in our sampled problem. The KRP structure enables us to efficiently be able to estimate these leverage scores. And we presented hybrid sampling, which allows us to more effectively work with concentrated leverage scores. And putting these together gives our algorithm CP alternating randomized least squares, which we saw on the Reddit tensor was between 12 and 16 times faster than the corresponding CP-ALS runs. I wanted to just end by mentioning that the paper is currently on arXiv, which has some interesting stuff about how you do the hybrid sampling specifically for the Khatri-Rao product structured problem. And I wanted to thank the CSGF for a great 4 years, and also especially for enabling my practicum, which led to this work. And now I'll open the floor for questions.